I'm going to describe how to use a multi-stage batch distillation simulation. This is a simulation that plays directly in browsers. And what we do is we charge a still with 10 kilomoles. So 10 kilomoles of a mixture. The mole fraction of the more volatile component is 0.2 in this case, and that was set with a slider. We also set the number of equilibrium stages, in this case 3, and the reflux ratio, L over D, where L is the liquid flow rate, D is the distillate flow rate. Now we're assuming that each of the stages is at vapor-liquid equilibrium. This may not be the case for a real system, but certainly first understand this idea of batch distillation, we're going to assume that. The simulation also assumes that the still has been running with the valve closed. We're not collecting anything. Instead, we're running at total reflux until we get to a steady state. Then when we hit the collect button, we'll collect the amount that we set in this slider. And each time we hit the collect button, we'll collect another, in this case, 1 kilomole. Anytime we can reset, go back to the initial condition. And we can do that up to 8 times or until we only have 2 kilomoles left in the still and the simulation stops. So it's important to realize that once we start collecting samples, this is a transient system, so the mole fraction of distillate, the mole fraction of the still, and the temperatures are continuously changing, and we can see that in the simulation. So I'm showing an X versus Y plot here, where the still, mole fraction 0.2, is what we set at the start, and you can see the distillate concentration is 0.83 at the beginning. So we're getting significant separation enhancement of the more volatile component. So let's look at the simulation and understand how things change as we change these variables. So here is the simulation, and you notice the highest temperature is in the still, 97, the lowest at the top. If I were to increase the mole fraction of B, the temperature drops. And the reason for this is that we're increasing the amount of the more volatile component, the component with the lower saturation temperature. You notice how I move the mouse over this curve, it explains what it is, and likewise for the X equals Y curve. And likewise, if I move the mouse over a stage, then it shows the composition and the temperature of that stage. Now, if I were to increase the number of equilibrium stages, then you'll notice that the mole fraction of the distillate goes up significantly. Now it's at 0.96. Let me now dial that back. If I increase the reflux ratio, we also increase the mole fraction of the distillate. So when I hit collect, then you'll notice the mole fractions are decreasing, both the still and the distillate. This is a transient process. And if I hit collect again, well, let me show you the behavior on the TXY diagram. If I hit collect, then notice the temperature is increasing and the mole fraction, again, the distillate and still are decreasing. So after 2 samples, the mole fraction in the still is down to 0.07. The other display would be the distillate container. So the first one, mole fraction 0.89. The second one, the mole fraction only 0.68. And if I continue collecting, then you'll see that this mole fraction now is significantly lower, and we have very little of the more volatile component left in the still. Temperature's up to 105 degrees. Now I can hit reset, go back beginning. I could collect a larger amount. I can change the reflux ratios, etc. Directions here have some of the same information that I explained in this screencast. And details show the mass balances used, the equations to determine these concentrations. So this equilibrium stage is multi-stage batch distillation.